he will tell us about optically levitated nanogram scale particles. Please, go ahead.
Great, thanks very much. And yeah, thanks to the organizers for the invitation. Apologies I can't be in person at this very exciting meeting, but it's great to be able to participate online. So yeah, I'll be talking about optical trapping of relatively large particles by optical trapping standards, at least nanogram masses, and then maybe telling you a couple of the features we run into as we start to try to use these particles for precision measurements like the ones we're all excited about here. So as just one slide of introduction into optical trapping in general, we've heard quite a few actually talks already this week showing all the nice things that are happening in the levitated optomechanics community generally, but I'll be really focusing on optical tweezers. And it's kind of amazing to me, at least, that you can trap particles from nano to micron sized and maybe even larger, which scales from femtograms in mass to even tens of nanograms in mass, more than 6 orders of magnitude, just by taking a laser and focusing it. Here's some examples of the traps we operate at Yale. For our small particles, which for us tends to be below about a micron, we form these tightly focused tweezers and trap at the focus of that tweezers in 3D. But we've also been working on going to even larger particles and gone back to the original traps built by Ashkin in the 70s, these levitation traps where we have a vertically oriented beam. The particle's still confined in the radial directions by the gradient forces, the tweezer forces, but in the vertical direction, its weight is balanced by the vertical radiation pressure of that upward propagating laser. So this allows us to trap a very large range of mass particles, and maybe what's most interesting for this audience here is, of course, if we're trying to see really tiny forces, as in the plot on the left, where our force couples just to the particle and maybe not to the mass of the particle, going smaller helps, and these femtogram masses, like the ones Marcus talked about at the beginning of the week, which are now reaching really the quantum measurement regime, are good for seeing tiny forces. But if we want to see things that couple to mass, like gravity, of course, what we're interested in here, the figure of merit tends to be to go to more and more massive objects. And our acceleration sensitivity, or our force sensitivity per unit mass, of course, improves as we go to larger masses. And on the optical side, this means nanograms. And then we heard from Hendrik and others that with magnetic traps and other levitation methods, we can, of course, even go heavier. And with tethered oscillators like LIGO, even heavier. So setting that up, let me just first show you the team here at Yale so I don't forget doing this work. So this is our group. We have an acronym we're called SIMPLE so that we can be a real precision experiment. And we're really interested in applying these systems to measurements in fundamental physics, particle and nuclear physics, as well as gravitational physics. But we're a relatively small team. We also heard from Gavin earlier this week about this exciting project we're getting started called MassQG, aiming to start to do a Pathfinder experiments towards ultimately testing if we can gravitationally entangle these particles. And of course, we're collaborating with Gavin at Warwick, Andy at Northwestern, and Anupam and Sugato on the theory side on that project. So back to this question of large masses. So in optical traps, it turns out that the limit to how large of a particle we've been able to trap is not so much the laser power we need to hold it up against gravity. Actually, with tens to maybe 100 milliwatts, we can levitate these objects as large as 30 nanograms in mass. But for the silica particles we tend to use, there's some stray absorption of the laser light, which as we pump the chamber to high vacuum, there's no longer any efficient cooling of the particle's internal temperature. And if there's any laser absorption, then eventually these things heat to 1500 Kelvin or something and melt or vaporize in the vacuum chamber. But up to these tens of nanograms of mass, we can actually, in the same levitation trap here, you can see we're trapping over two orders of magnitude in mass and a factor of more than 10 in particle size. And this is nice because, as I said, as we get to these larger particles up around a nanogram, we've been able to demonstrate acceleration sensitivities here approaching the hundreds of nanogs per root hertz. So this is still far from the quantum limit, and I'll say a little bit more on that in a second. But we're starting to get to actually relevant sensitivities, force and acceleration sensitivities for trying to test some things about gravity with these optically levitated systems. So why aren't we at the kind of standard quantum limit like you might be with the femtogram mass sphere as well? The kind of dirty laundry here is on the left. For these levitation traps, the nice thing is we can lift large objects, but they kind of naturally operate at very low frequencies because we don't want to use so much laser power to stiffen up the trap and melt the spheres. So that means we're working below 100 hertz. And if you look at our measured, let's say, force noise spectrum here, in blue, you see there's all kinds of noise lines and vibrations and other pointing instabilities that show up here at low frequency that we have to contend with. So there's a lot of technical noise that we're still working to eliminate and we're making progress on, but is already maybe reaching interesting sensitivities and a few orders of magnitude from really trying to get these into the quantum measurement regime. Okay, so to show you a little bit the flavor of the experimental control we have over these particles, these larger mass particles are maybe a little different than most of the femtogram mass spheres people are using in the community. With large particles, we can actually pick up the particle we want by putting them on a glass slide, moving our laser over top, and actually this image here, when you see it in focus, it's sitting here on the glass slide. We're shaking that slide with the piezo, and it's actually popping up into the laser and trapping just above the focus. That's where you see it out of focus, and then we can actually set the same particle down, pick it up over and over, so that if we get a really nice particle, we can repeatedly load the trap, and then remove the cover slip away to have a clean, unobstructed beam. We do this in about a millibar of gas so that we have enough damping that the trap's stable. But once we have a particle trapped, we can pump down to high vacuum pressures. And a key for any sort of measurement that wants to measure weak forces like gravity is to be able to get rid of all the other stray forces. We've heard a little bit about this week, but maybe it's going to be the focus of my talk, so I'll talk about it in some detail. And as we start to try to do any real measurements with these optically trapped particles, the first thing we always see is their charged coupling to stray electric fields. So we need to neutralize them. It turns out when we pull the glass spheres off glass, there's triboelectric charging, or like rabbit fur on glass sort of charging. And we typically have maybe 1,000 to 10,000 extra electrons, always electrons on the sphere. But we can apply an oscillating electric field and measure the motion of the particle, which allows us to infer its electric charge, and then flash UV light to discharge it, knock electrons off the sphere here over some time. And you see we actually cross zero here, which means we've gone too far. So we now have more protons than electrons on the sphere. But now we can change the electric field a little bit, so we're primarily knocking electrons off the gold surface, back onto the sphere and go the other direction. And if we zoom in here at the end, you can see in this relatively small electric field, we see these really nice discrete steps that correspond to knocking one electron at a time onto the sphere. And when we get to zero here, we know we have exactly the same number of electrons and protons on this kind of nanogram sphere with 10 to the 13, 10 to the 14 protons in it. So this is a perfectly neutral object, at least for its monopole charge. I'll come back later to multipole moments in the charge distribution. The next thing we do is we can spin the particles. So we actually use circularly polarized light to optically spin these, in this case, silica particles to megahertz frequencies. In high vacuum, because there's such low damping, actually if we trap them in circularly polarized light, they absorb a tiny amount we transfer a tiny amount of the angular momentum from that trapping beam to the particle. And over kind of day-long damping times, they spin faster and faster to their terminal velocity. And here's a silica sphere, 10 to the minus 7 millibars, spinning up to a terminal velocity just above 4 megahertz. So this thing's spinning, 4 million times a second. That actually gyroscopically stabilizes these objects. So if there's any asymmetry in the multipole moments of the charge distribution that's left, it averages over those. So they have an electric dipole moment pointing in the vertical direction at that point. And that dipole moment is going to be vertically oriented and gyroscopically stabilized. So I'll come back to this later when we do measurements. I'm pointing this out here just because even though I said these were neutral, they have exactly the same number of electrons and protons. These stray dipole moments are going to be a dominant sort of background when we try to do gravitational measurements. Okay, so now we have a perfectly neutral spinning sphere at a megahertz, gyroscopically stabilized. If we want to, we can cool the center of mass mode. As far as I'm aware, this is still the state of the art for kind of nanogram mass objects, mass optically levitated objects. This is a plot of the amplitude spectral density of the sphere's motion in one of the directions perpendicular to the trapping beam in meters per root hertz. So this is a nanometer here in the center of the plot. And again, we have a relatively high Q resonance here below 100 hertz. When you have the minimum amount of damping, we just apply active feedback, cold damping of the sphere's velocity to cool its motion. And as we increase the gain in that feedback loop, you can see you can cool to the yellow, blue, and then red curve. And at our current displacement sensitivity and noise floor, we're cooling to about a 50 microkelvin effective temperature. Now, this is very low frequency, so this is still several orders of magnitude from ground state, but this is corresponds to a relatively good detection sensitivity for these spheres. And then I'll come back to this in more detail, but if we want at this point, we can also control the orientation of the sphere. So we have this, again, gyroscopically stabilized spinning sphere with a dipole moment pointing in one direction, and we can apply electric fields, kind of the classical analog of a pi pulse, or any kind of torque we want to maybe orient the dipole moment and maybe try to average away the effects. And I'll tell you more about this paper in a few slides. Okay. So that's all for single spheres. In our group, we're actually quite interested in also making arrays of spheres for various applications, but so we can look at sphere-sphere interactions eventually as well. And we've recently upgraded the sorts of traps I'm showing with high-power lasers so that we can trap up to 10 by 10 arrays of microparticles in vacuum. We have FPGA code, essentially that for these large particles, because the traps are quite slow, we can just stroboscopically illuminate each of the traps in series with an acousto-optic deflector. So we have an AOD and then an FPGA that's applying different tones to raster the beam through the array of particles. And because we can go over the array many times before the inverse mechanical frequency of the particles, before the particles feel that the beam's been moved, this just looks like a stable trapping potential to the particles. And it eases some things to do this time domain multiplexing in terms of imaging the particles and being able to, in our FPGA, detect each particle individually. So we now have this working at least in relatively moderate vacuums around a millibar, where we don't yet need to do the active feedback stabilization and cold damping I was showing on the previous slide. And here's just a picture of a 5 by a 5 array of spheres that we've trapped in about a millibar of pressure. It turns out that actually the main challenge we've had in loading these arrays with microparticles, especially in a dense configuration, is again the kind of electrostatic forces and electrostatic interactions between the particles. And as I said, when we shake the spheres off, if they have electric charges of order 10 to the 4 electrons, and since they're triboelectrically charged, they always have the same sign. There's a significant repulsion between the spheres as they're falling down, and we might load some particles in the array, but then when we shake again, the next batch of particles falling in knocks out the ones that are already there. So this is showing the sphere-to-sphere Coulomb potential versus their separation, and at separations of maybe 100 microns at our initial charges, we're way above the kind of trap depth of the optical trap. So the Coulomb forces are just completely dominating and knocking spheres out. So we've found so far the best way to get relatively large numbers of spheres trapped simultaneously is to kind of discharge them in flight. So since we're doing this at about a millibar, we can make a plasma just with a high voltage electrode, which is making copious amounts of ions and electrons that then neutralize the particles as they're falling, and we get their charges down to maybe around 100 electrons, which is sufficient to let the optical forces dominate and load these into the spheres. Into the traps. But we're still working to improve that loading efficiency. And like I said, even though we have laser power for a 10 by 10 array, maybe we're typically only getting, a quarter to half of that array filled with our current loading system. So we want to keep pushing on that. But of course, if you're going to be putting spheres in here and looking at interactions, maybe eventually gravitational interactions between them, you still need to worry about these Coulomb interactions. Again, I'll show the numbers later, but even with one charge on the spheres, the sphere-sphere interaction is maybe like 11 orders of magnitude larger than the gravitational interaction. So you can keep in your mind that gravity is even 11 orders of magnitude off the bottom of this plot. So it's a real challenge if we have any stray electrostatic forces. But if I can start this new UV, oops, let me just play. You can see we have full control. This is an array of optical tweezers. So we can make the obligatory kind of Yale Y here so that you can see we can move these things around, trap them, and then reconfigure the array at any distance we want. And yeah, so that's the Yale Y that our student Ben Siegel made. So in our group, as I said, we're quite interested once we have these technologies in applying them to fundamental physics. And historically, we've done lots of things in our group. I'll talk mostly actually about these first two kind of applications. So testing Newton's law at short distance. We've heard about this already several times this week. This is a really important experimental measurement, even before we ask, is gravity quantum? Do we actually understand that Newton's law holds to arbitrarily small objects? And I'll also talk about testing the electrical neutrality of these particles. So once we have them neutral, how neutral are they? And even though this is maybe not a gravitational measurement, it shows, I think, some of the effects that start coming in as you try to eliminate all the electrostatic forces in the world and see things smaller than normal kind of stray electric charges. And I won't talk about this, but I'll just highlight we've recently been able to do things like look for certain models of dark matter scattering from these spheres. And in fact, the sensitivity is good enough that we can plant single radioactive nuclei into these micron-sized spheres and see the recoil maybe as a single alpha particle leaves. We see the entire sphere recoil by momentum conservation. So we have some recent work on that too that I won't mention. Okay, so let me start with this. Actually, the second of these is testing the electric neutrality of matter, kind of as a segue into trying to do real gravitational measurements. So it's actually an interesting question to have if you have a ball with maybe a sphere here with exactly the same number of electrons and protons. Does it really have exactly zero net electric charge? And a non-neutrality of that sphere could arise maybe from two different mechanisms. There could be a tiny difference in the sum of the electron, proton, and neutron charges from zero. It's known to extreme experimental precision, in fact, that the sum of these charges is less than 10 to the minus 21 elementary charges. That's a lot of zeros. But in the standard model, maybe there's no deep symmetry between the quarks and the leptons that guarantees that things have to be charge neutral, especially if you make additions to the standard model. And so looking for, additional digits of precision and how close the quantization of charge actually is for the leptons and baryons is actually quite interesting. And then maybe another kind of more modern proposal is that, of course, most of the matter in the universe we think is dark and we know can't have order unity electric charges, but can still have an electric charge or an apparent electric charge from maybe just mixing of some dark forces with the standard model that's much less than one elementary charge. And in general, these particles could form bound states, especially with positively charged nuclei in normal matter, if dark matter thermalizes with normal matter. So we could search for maybe strange, funny nuclei that have a heavy milli-charged or microcharged dark matter particle orbiting them in a Bohr-like atom. And actually, people have been thinking about this recently. So here's a paper from Maxim Popslov and Hari Ramani showing that you can calculate or estimate both where you would get stable bound states, and maybe they've done some impressive estimates of what the terrestrial density of such dark matter particles might be. And it turns out that if you look at the accelerator constraints, this is the charge of the fractional charge of the dark matter particles in units of an elementary charge. So this would be a millicharge, a microcharge, versus the mass of the particle. You can actually form stable Bohr-like atoms here with positively charged nuclei kind of in this region. And there's a lot of unexplored space from accelerator searches, which are up here, as well as underground dark matter detectors where we wouldn't yet have seen these kinds of dark matter particles in existing experiments, but maybe we would just pick them up as a tiny, funny fractional charge in normal atomic matter. And actually, it turns out these can be quite sensitive, and if even only, with our current sensitivity, if only a fraction of, less than a part per million of the relic dark matter in the vicinity of the Earth were carried these kinds of tiny milli or microcharges, we might be able to detect it. So the experimental measurement is really quite simple. You just neutralize the microsphere like I was talking about, so we're sure we have exactly the same number of electrons and protons. And then we apply as large an electric field as we can and look for any force on the particle that could come from a stray electric charge. Now, of course, it's easy to say that, but then what is the real challenge to doing this measurement? So I'll be talking about these results from a few years ago, and maybe this is prescient for trying to do gravitational measurements in that we don't measure what we expect, and we see backgrounds, of course, when we try to do these very precise measurements. And these backgrounds kind of overwhelmingly come from conventional electromagnetic forces, not interesting new fractional charges, but just stray charges that we aren't controlling. So the first thing we see is, as I mentioned, even though we know we have exactly the same number of electrons and protons on this object, there's still, in general, a multipole moment, a non-zero set of multipoles in that charge distribution, in particular the permanent dipole moment. And we are, in this example, spinning the microspheres. And one of the main reasons we like to spin the microspheres is to minimize as much as possible the torques that act on this dipole moment in this experiment. So of course, if you have a permanent moment, even if it's averaged away, there's still some permanent moment in the direction of the spin axis. And we start applying an electric field, maybe perpendicular to that spin axis, to attempt to measure the net charge of the particle, there's going to be a torque. And if the particle is at all aspherical or has a little asphericity, then that torque can cause rotations or precessions that then appear to us to look like apparent motion of the center of mass, just due to kind of our imaging system being fooled by these stray torques showing up as motion. And this is really why we need to spin them as fast as we can. Actually, this plot on the right is showing that if we apply this oscillating electric field and just measure the apparent charge we see, so essentially what our imaging system tells us the center of mass is moving by, as a function of that spin frequency, once we get it neutral, it doesn't look like it's perfectly neutral. It actually looks like it responds to an electric field as though it had 1/100th of an elementary charge on it when we start. But as we spin it faster and faster, we can actually get down to millicharge kind of apparent forces on it. So we see it moving, and this is presumably torques, and the reason it cares about the spin is that we're gyroscopically stabilizing it better and better, so these precessive motions are smaller, but as we spin as fast as we can and start to be limited by other things, we start to see this roll off around 1/1000th of an apparent electric charge. So what we said was a neutral object is not behaving as though it was a neutral object, of course, because of this multipole moment, and this is maybe a specific case where gyroscopically stabilizing it really helps. Okay, so once we get it spinning up to megahertz, the next thing we have to worry about in this experiment is vibrations. It turns out we were initially a little bit fooled by this, but when we apply the electric field that's applying this 10 kilovolts per millimeter oscillating across the sphere, that comes through a feed through on our vacuum chamber. And we've measured with no sphere in the trap, if we just apply this oscillating electric field, the whole, almost inch thick or 2 centimeter thick stainless steel window on our vacuum chamber is shaking due to electrostatic forces from the dielectrics, the force on the dielectric in the high voltage feed through to our chamber. We can measure this quite nicely, and actually, unfortunately, we get a vibrational peak from that electric force on the chamber that's quite close to the sphere response. So we have to worry not just about vibrations from the room, but really the electric forces we're applying in this experiment shaking things around. And so in this case, we actually added a second monitor beam, which is co-aligned with the trapping beam. It just misses the particle, but goes through all the optics and everything else and can measure the vibrations independently of the sphere response and subtract out those vibrations. So vibrations are very challenging. And then maybe last but not least, because in the end, this is really the thing we think that limits us is real forces on the dipole. So above I talked about torques, but there's still forces that really are moving the center of mass of the particle that come from gradients in the electric field. So we try to make our electric field as uniform as possible. We align these plates here that are applying the field to kind of milliradian precision in this experiment, but we still have some gradients, and even after our best job that we can do to minimize them, our COMSOL or finite element simulations indicate we can get maybe part per million sort of kind of uniformity in the electric field, but then that gives us this force that corresponds to this, 1/1000th of an apparent electric charge. Or maybe we can get it a little bit lower as we optimize things in this experiment. So this is kind of a laundry list, but points out that, everything is hard. And for this specific experiment, it's really these dipole moments that are causing us the biggest problem. That said, though, we can push this through, and we actually search for fractionally charged particles in a relatively large mass for this field, about 76 nanograms of total mass. Um, we did see, of course, residual forces that are consistent with stray forces on those electric dipole moments in the particles, but that lets us set still conservative limits on the abundance of fractionally charged dark matter particles in these spheres, and down to fractional charges around 1,000th of an elementary charge. We can say we don't have any in about 10 to the 17 per 10 to the 17 nucleons in our particle, and our sensitivity maybe extends at less abundance sensitivity down below 10 to the minus 4 fractional charges. And again, I'll maybe go quickly over this, but the plot on the right is just showing if you interpret this in terms of a kind of dark matter model where dark matter has a fractional charge, builds up on Earth for charges, again, in this kind of milli to tenth of a milli elementary charge versus the mass of the dark matter particle, we're able at this abundance sensitivity to kind of search in this entire parameter space above the blue line here, which is quite complementary to the previous searches that have been done at accelerators and fixed target experiments for these kinds of milli-charged dark matter particles. So unfortunately, we don't see anything, at least inconsistent with our backgrounds, but we're probing interesting parameter space that hasn't been looked in before. Okay, so with all that said, maybe I'll move on to the maybe more directly relevant thing for this meeting, which is, can I measure tiny forces between masses, real gravity-like interactions, and then eventually gravity between micron-sized objects. So, of course, Marcus talked about this. I believe Giorgio thought might be talking about just before this, but there's quite an interest in the community in taking these optically trapped or otherwise levitated objects and trying to measure gravitational forces. And in particular, at the micron scale, we really haven't yet measured gravitational strength forces between objects of smaller than what Marcus has done now, kind of millimeter scale, pushing down to tens of micron scale, and we haven't measured gravity at those distance scales at all, even in large torsion balances below about 50 microns. So it's still quite an open problem of whether we can measure gravitational strength interactions in the absence of any other background forces at these scales, let alone do all the exciting things we want to do in this meeting of testing the quantum nature of those gravitational interactions and eliminating decoherence at the same time we start to test those interactions. So this is actually what really got us into this, at least myself, working in Giorgio's group, trying to measure deviations from Newton's law or search for deviations from Newton's law at short distance at the micron scale. At Yale, we've actually implemented a new kind of method for doing this, which I'm showing some pictures of here, where the idea is that in many of these experiments, the challenge is that if you want to modulate a mass density next to the sphere, so in the previous experiment for milli-charged particles, it's quite easy to apply an oscillating electric field and then lock into that oscillation to look for a force at that frequency. It's much harder to apply an oscillating gravitational field. And the typical way you want to do it is to make different density materials and move them next to your sphere. But of course, when you have those different density materials moving next to your sphere, you can induce vibrations and other things that cause real accelerations and forces on the particle that we want to avoid because they show up as backgrounds in these measurements. So the idea we had at Yale was to take a microfluidic capillary, coat it with gold so that you screen all the electrostatic forces, but then send micro droplets of different density fluids through this capillary. And we can send these by at tens of hertz next to the sphere, have a sphere levitated just off the surface of this capillary. And this capillary has a very thin wall, about 5 micron wall, and then a gold coating around that wall so that we could have a very low vibration, continuous way of moving a varying mass density next to the sphere. Then, of course, we can look at the modulating force at the frequency of those droplets as they go by. So we've done this. This is a levitated 5 nanogram sphere that's levitated about 2 to 3 microns from the surface of the capillary. You can't resolve this in the microscope image, but we're able to calibrate that and know very precisely the distance. So this is the side of the capillary. It's gold coated. So you just see a blob there and then the sphere floating just off its surface. And again, that's about 100 micron diameter capillary with these different density fluids moving in it. Here's a view of the capillary itself before we put the gold coating on it. And here you can see we have these 200 micron long interspersed drops. In this case, it's oil and water, but you can do it with other immiscible fluids, eventually like liquid metal and oil, to get as much density contrast as possible. And then we have fibers here, which are monitoring the droplets going by so that we can tell, we can interpolate the sphere sitting here, and we know the mass density pattern going by the sphere at any time, and we can correlate that then against the motion. So this is still definitely a work in progress. We've implemented our first version of this experiment, but the maybe bad news and cautionary thing about these types of experiments trying to measure gravitational forces is that, likely these sorts of dipoles coupling to some tiny breathing of the capillary as those droplets are going behind it are producing stray forces. And in fact, those forces are something like 10 to the 8 times larger than the gravitational force we want to see. So even though we have the force sensitivity in principle with these spheres when they're floating out in the middle of the vacuum chamber all by themselves, when we bring them next to these surfaces and then start moving a mass density nearby, we start to see background forces that are really challenging to handle compared to the strength of gravity. So this is, we're still working on it, and we want to add kind of more shields in addition to the gold shield of the capillary itself, a kind of freestanding membrane between the capillary and our particles. But we're still maybe not even quite at the best sensitivity from the torsion balance experiments. And, Giorgio's group has also been working on a parallel experiment here to push down past the torsion balances, but then to reach actually Newtonian strength gravity is still quite a challenge ahead. Okay, so what's really the problem here? So I've said it a couple of times, but let me say a little more about the details of what we're seeing in these experiments. Essentially, the stray electric forces are the dominant challenge when gravity is so weak compared to electromagnetism that any amount of stray charge and multipole moments is really causing huge forces by the standards we care about. So we've done some work, and also Giorgio's group has done quite a bit of work in this area as well to actually characterize what are the dipole moments of real objects, micron-sized objects that you might trap in vacuum. And the technique we've used for these large silica spheres that we use in our lab from 10 to the 20 microns in diameter. This technique was just invented by Giorgio's group, but it's relatively straightforward. We just allow ourselves enough electrodes that we can rotate an electric field. So we have a rotating electric field. For a strong enough field, actually the dipole moment will align with that electric field due to the torque. So it'll line up, and then you'll have some librational motion in the rotating frame. The dipole will oscillate around that rotating field. So we can do this electric rotation and then look at side bands of the motion that show us these librational peaks. So each of these peaks here is just a different electric field amplitude. Depending on the amplitude of that motion, we get a different oscillation frequency for the libration, and we can pretty precisely measure the librational motion, which then tells us about this dipole moment. Kind of interestingly, we see something that goes both linear and quadratic in this electric field, which you might not immediately expect, which implies there's both an induced libration from the force, from the torque on the permanent dipole, but then also a torque on the induced dipole from the field, which might happen if there's some lossy surface conduction in this dielectric. So the silica, at least these small silica spheres, maybe due to surface layers of water or other things, are not acting as perfect insulators likely. But we can infer from that then the total size of these dipole moments, which then also depend on the frequency and everything else. And there's a permanent dipole in these units at the thousands to tens of thousands of e microns. So just to put that in text in these spheres that might have 10 to the 15 or 10 to the 15 or 10 to the 16 electrons in them, roughly 1,000 to 10,000 of those electrons are offset from the charge distribution by about a micron, if you want to think of it that way. And then there's also some non-negligible induced torque that we can see as well that comes from maybe some surface conduction on the spheres. So this is maybe the input that to then estimating, how bad these kinds of dipole moments are going to be for other experiments as well, including gravitational measurements. And so, this is only partly our work, but it's not just us who have measured dipole moments in levitated particles. As people are using these more and more for precision measurements, a number of groups, actually, to my knowledge, starting in Giorgio's group at Stanford, has measured kind of dipole moments just using the method I just said for kind of 100 picogram mass spheres, 5 micron diameter spheres. These are the measurements I just showed for somewhat more massive, up around nanogram mass spheres. And then I'm aware of one measurement from the Tokyo group for femtogram mass spheres down here. And this is just an upper limit from Tongkung's group. I think he'll talk maybe tomorrow about Paul trapping diamonds, nanodiamonds in high vacuum. This is an upper limit because there's diamonds, because they're in a Paul trap and an RF trap, they're not electrically neutral. So some of the dipole moment could come from the net charge on the particle, but this is some upper limit of what the dipole moment might be for a perfectly neutral particle. And maybe it's interesting, although there's really only one point driving this, so one should be quite careful about this, but you might think that you're seeing that these dipole moments in the measurements are scaling roughly with the mass or the volume of the particle. So it might be something baked into the particles themselves, at least for silica, rather than something on the surface, but we definitely need to do more study of this and try to understand in real materials, especially maybe the diamonds or other materials that would be relevant for gravitational tests with, quantum sorts of gravitational tests. What are these stray charge disorder in the objects going to look like? But, if we take this as inspiration and roughly, kind of take this very rough extrapolation of what the size of those dipole moments might be, we can put in some numbers for the kind of how big are the dipole-dipole interactions or just the back of the envelope electrostatic interactions between spheres. If you want to imagine seeing gravitational interactions between two isolated spheres, radius r separated by distance d. I already talked about this, but as we all know, you can't have any net charge on the spheres. If I put even one electron on both of those spheres for 10 picogram mass spheres, kind of micron-sized spheres with radii, around a micron, separated by some distance. Here it just scales out because they're both 1 over our potentials. The Coulomb force is, this 5 times 10 to the 10 times bigger than the gravitational force. So we know this, and luckily with levitated objects, we can control their charge precisely as I showed and keep them neutral. So we really don't have to worry too much about this, but we can't have any charge on the spheres, obviously. The real issue, though, is even when you get these neutral, then they're not perfectly neutral, of course, due to the multipole moments. And if you look at the dipole-dipole interaction energy compared to the gravitational potential, again, plugging in the numbers and actually a little optimistic compared to that volume extrapolation on the previous slide, it's not 10 orders of magnitude smaller. It's maybe only 4 orders of magnitude better. So we still have a factor of order 1,000,000 that we need to shield with a freestanding shield between these objects or suppress by minimizing the dipole moments of these objects to suppress these interactions, just like we do in all the kind of professional 1 over r squared gravity tests we've done to date. But of course, for quantum tests of these gravitational interactions, this is possibly even harder because not only do we need to screen the interaction, but we need to avoid decoherence or which path information being leaked out by introducing the shield and having maybe electrostatic interactions with the shield, which would be fine in just tests of Newton's law, but would be catastrophic for these kinds of quantum experiments. So this is still definitely a challenge, and we're quite interested in our group in pushing harder on this and seeing what's achievable here. I'll just quickly say in the last minute that we have done a little bit of work on this, as I indicated. Once we have these things spinning and have their dipole moment oriented, we've shown we can do essentially like classical pi pulses, where we apply a torque from the electric field, the applied electric field that rotates this dipole moment down. And actually, if you look at the spinning frequency of these, how much they're accelerating, spinning faster or slower as we rotate them up and down, as we turn it over compared to the circular polarization of our trapping light, we see very nicely that they speed up or slow down, speed up or slow down. So we really are flipping these things over. And then when we apply an electric field gradient on purpose, we see some force, and we can actually, depending where we are in this oscillation, we can cancel out that force. And here we're just showing maybe we can, if you look at the scales really carefully here, we're applying a femtonewton scale force, and maybe we're canceling that by about a factor of 100 by time averaging over the orientation of the dipole moment. And so one could think whether there's some analog of this you could use in a quantum experiment, some analogy of dynamical decoupling or something like this for getting rid of effects of dipole moments if we can't make perfect objects with no charge disorder. Okay, so let me just stop there. I'll summarize that I think these kinds of levitated systems are really interesting. It's exciting, especially at this meeting, to see people talking about doing extremely ambitious things and testing gravity and the quantum nature of gravity with them. But of course, when you start doing experiments, there's non-fundamental things that are quite hard, especially conventional forces from electromagnetism and stray charge. And so in addition to all the great work we need to do to put these objects in quantum states and avoid decoherence, we still need to minimize these kinds of electrostatic interactions as well. And hopefully we'll make lots of progress on this as a community in the coming years. So thanks very much.
Questions? First,
Thanks. Hi, Dave. Nice talk. Do you think there's something you can do with the materials? I mean, can you somehow, for example, heat the material so it sort of becomes for a brief period of time molten and maybe, I don't know, maybe you'll lose charges? Or consider using something like a coating of indium tin oxide to sort of at least equalize the distribution of charges on the surface? So just interested in you've thought about those sorts of things.
Yeah, excellent. Yeah, so my feeling is yes, we just haven't done it or tried it yet, in our group at least. My guess is there's lots of improvements one can make on the material science side. If this is really scaling like volume, maybe it's some real defects built into the kind of Swiss cheese silica we all use. So making good high purity crystals or other extremely pure materials might help. And then once you get the best material you can, I think it's going to be an all of above approach. You might be able to anneal the charge distribution somehow and make it more spherical. So some of the things we think we've seen is that the charge is a little bit mobile in these spheres, and maybe spinning them in high electric fields actually makes the charge distribution become more uniform, although we have to really prove that's the case. So we want to study that in more detail. As you say, thermal annealing is very interesting. If we can make the charge more mobile, maybe it wants to spread out and minimize these dipole moments. So yeah, I think this is really early days, and there's lots to study, and hopefully there's a single solution or some set of many solutions that really improve things.
Anupam?
Yeah. So thanks, Dave. Yeah, very nice talk. So I mean, if you want to have my opinion, I don't think the electromagnetic interaction is very important, but as you know that there are also ways of shielding the electromagnetic interaction. So that's something good which happens in the case of electromagnetism. So maybe some of the things which I think you're discussing can be also be shielded if one does things carefully. But my point is that is there any way, have you also, or is there any way one can try to say cool the system, cool the bulk itself? Like let's go to say, I don't know, maybe sub-Kelvin level, millikelvin level, and then do this kind of experiment to see that what extent the dipole moment and other properties, how do they behave as we go, not only with the volume, but also cooling the system itself. Do you have any opinion?
Yeah, so just to echo what you're saying, I definitely think shields, like there's no gravity experiment I'm aware of that doesn't have an electrostatic shield to shield these forces. So I definitely think we're going to want that. But because you still have sphere shield interactions in these, especially these quantum experiments, you're going to have to be extremely careful about how you do that shielding. And if you don't get rid of the dipole, there's going to be a dipole image dipole interaction from any good shield, right? So we have to be very careful. So that said, I completely agree. We'll definitely shield them, and we should work hard on that. Then to the question of cooling, I think I just don't know. I mean, I don't, Peter was suggesting maybe the opposite of heating them to anneal the dipole. Once we got them really hot and anneal it, maybe we can cool them and freeze the charge in place. I think these are all completely open questions, but I don't think it's not obvious to me that you just cool down the spheres we have and the dipole problem goes away. They probably, you lock in the charge distribution at some level and still have to deal with it.
Thanks.
Further questions? 1, 2, 3. Thank you very, very much. Then let's thank the speaker.
Thank you.
And we pause for lunch. We'll be back at 2 o'clock, right?